Okay, so let's wait 1 more minute so that everyone's here. I see the numbers are growing. Okay, so maybe we could start. So that's the beginning of the second week of this conference, and it's really a pleasure to start this new session with Professor Eva Andrei, who is an experimental condensed matter physicist, who's known for her work on low-dimensional electron system, including 2D material. And she's now a professor at Rutgers University, and she's also Betty and Gordon Moore Foundation experimental investigator in quantum material. And she did a very pioneer work in electronic properties of graphene, in particular showing this very high mobility in suspended graphene, like a decade ago. And now she's gonna talk about her activities in flat bands and correlated states in 2D crystal. So thanks a lot, Eva, for being here, and the floor is yours.
Hi, good morning, good afternoon, and thanks the organizer for putting together this marvelous conference. Since its discovery in 2005, graphene and other two-dimensional materials have kept many of us busy. In my case, every time I thought, okay, graphene has already yielded all its secrets, it's time to move on, a new discovery came along to keep me in, fractional quantum Hall effect, Van Hoff singularities, atomic collapse, Kondo screening, superconductivity more recently, and Chern insulator. So the system is extremely rich. And there are two reasons why it is so rich. One, it is because being one atom thick, this graphene and other two-dimensional systems allow us to change the band structure without changing the chemical composition. And the second reason is because they're just two-dimensional and it has very few electrons. So it is possible with a relatively small gate voltage to change the position of the Fermi energy. And why are these things important? First is because we can make flat bands, and flat bands are nice because when you bring the Fermi energy within a flat band, interesting things happen that are due to correlations. And then more recently, we found out that you can reveal the topology of the band topology. So what I'm going to tell you about today is about two flat band systems and correlated states. One is in Moiré systems in two-dimensional in bilayer graphene, twisted to a magic angle, and the second one is periodic strain in superstructures. And here are the people who did the work, and the photos are the pictures of people who actually did the lab work here at Rutgers. On the left are our theory collaborators, and on the right are collaborators who supplied the boron nitride and the graphene on niobium diselenide. So just to define what I mean by flat band, if you look at, if you bring together a bunch of atoms and arrange them in a Bravais lattice, if you get a band for every atomic level that contains, that is made up of block wave functions that are all labeled by the quasi-momentum K, and all these Ks in the band make up the Brillouin zone. Now, there are two energy scales in this problem. One is the kinetic energy for hopping in between atoms, which we label by T, and the other energy is the cost to put 2 electrons in the same lattice, which we call U. And the competition between these 2 energy scales gives rise to the physics, the band physics that we all know and love. So when the Coulomb energy, when U is much smaller than P, which is what defines the bandwidth, then we have a very simple parabolic band structure, and everything in front of P square we call an effective band mass, nothing to do with the electronic mass. It just tells us about the curvature of this band. Now, in the other limit, when U becomes comparable to the bandwidth or to the kinetic energy, we can bring the Fermi energy within this band, then interesting things happen because the electrons can rearrange themselves to lower their energy by opening a gap here at the Fermi energy. And that's how we get correlated states. For example, so in this flat band, because the kinetic energy is quenched, the Coulomb energy can determine the electronic properties, and there are all sorts of correlated states that we can get and imagine: superconductivity, charge density wave, Wigner crystal, Mott insulator, and magnetism, and more. One very interesting predictions that was made by the Finnish group here is that if you have superconductivity in a flat band, you can actually, it is possible to achieve room temperature superconductivity. This is a very intriguing and possibly controversial prediction, but it would be something that is worth pursuing. Now you can say, okay, we already have flat bands. Landau levels are the quintessential flat bands when you put a magnetic field, for example, on graphene. And when you bring the Fermi energy within this flat band, you get very interesting correlated states, a fractional quantum Hall effect, or magnetically induced Wigner crystal. This is all very nice. However, this is not helping us if we want to achieve superconductivity, because breaking the time reversal symmetry with the external magnetic field is not conducive to inducing superconducting state. So the question is, can we create flat bands without broken time reversal symmetry? So for that, there is a very simple recipe to create flat bands. Take your standard parabolic band and put the material in a periodic potential with a period L here that is much larger than the lattice spacing. And what will happen, you break up your Brillouin zone into mini Brillouin zones here, and the band, and you get mini bands that are much narrower. So the larger the period here is, the narrower the band. So in the limit or very large period, you can get a flat band. So this is a very simple recipe. So how can we go about it? So there's 2 things that we need in order to accomplish this. One is we need to be able to change the band structure. You need to have a material where the band structure can be changed by an external potential. And secondly, you need to find something that will do the job of an external potential. So that brings me to graphene, which is our quintessential 2-dimensional electron system. Graphene is a honeycomb structure. Notice that this is not a Bravais lattice. It consists of 2 interpenetrating triangular lattices, the red, which we call A, and the green that we call B. And therefore, you don't have a single block function describing this state. And therefore, you should not expect having a nice, simple parabolic band structures. So the ingredients that go into the band structure are these four very simple ingredients: the fact that it's 2-dimensional, the fact that it's a honeycomb structure that is not Bravais, the fact that we have identical atoms on these 2 sublattices, and this is critical because it preserves in-plane inversion symmetry, and finally the fact that the hopping nearest neighbor hoppings are all the same. Now notice that none of these conditions says that we have to have carbon. In fact, you can achieve the same band structure with many other things, with cold atoms, with molecules, even with microwaves. And the band structure, the low energy band structure that you get looks like these two cones, which we call Dirac cones. It is described by this Dirac Hamiltonian, which is extremely simple. It's a one parameter Hamiltonian that depends on the single parameter, which we call Fermi velocity or the Dirac velocity, which is simply the hopping term T times the lattice spacing. And sigma here is the Pauli matrix, except that it operates on the sublattice degree of freedom rather than the spin. And the momentum here is measured with respect to the corners of this Brillouin zone. Now, in fact, we have 6 cones here, but only 2 of them are non-distinct. All the others can be reached by reciprocal lattice translation. Now we should notice that sigma dot p here is the chirality operator. The Hamiltonian is in fact made up of this chirality operator. Notice that it has opposite signs in these two valleys. In other words, is that going from one valley to the other, you need to change the chirality of your quasi-particles, and that gives you selection rules, which for an experimentalist is very important because there's no backscattering, and that's why you have such high mobilities in graphene. Another properties are the symmetries. There are 3 discrete symmetries that protect these Dirac points. Normally, when you have crossing of bands, as are these Dirac points, you open gaps. However, in this case, the Dirac point, the crossing point, is protected by 3 discrete symmetries: in-plane inversion, time reversal, and threefold rotation, and therefore these Dirac points are very robust. As for an experimentalist, this is important because we can't open a gap, we can't make a transistor out of this. Now this conical band structure translates into a linear density of states that vanishes here at the Dirac point. What this means for an experimentalist is that we have very few electronic states here when we sit at charge neutrality. In other words, it's very easy with just a little bit of voltage to move your Fermi energy up and down in the electron or hole sectors. So if you make a device like this, a standard device, you put your graphene on a silicon wafer with a 300 nanometer oxide layer, and you apply a gate voltage, you can walk with your Fermi energy in this band going from the electron sector to the hole sector with just a little bit of voltage. So 1 volt here buys you 7 times 10 to the 10th electron per centimeter square, and can take you pretty far up in the band structure here. So here again are the ingredients that go into this, into the band structure. These are purely geometrical. The band structure looks like this when we go away from what I showed you before was zooming into low energies. And this, so this series of conditions gives you an idea of how to modify the band structure without changing the chemical composition. For example, you can relax the conditions that all the hoppings are the same by, for example, strain. You can impose an external potential now by using a substrate or an electric field. You can put in point defect, and that develops magnetism. You can apply an electrostatic potential when you have a bilayer opens a gap, or you can apply a magnetic field that creates Landau levels. So there's many handles that we have here to change the band structure. Okay, so one handle that is now have become very popular is the Moiré system. Okay, I have a plan. Let me go back here. Okay, so when you superpose 2 graphene layers and rotate them a little bit, and most of you have seen this already many times, you create a Moiré structure here with a period that's inversely proportional to the twist angle here. And okay, so remember what we are after is we want to impose an external periodic potential. Can this Moiré structure give us a periodic potential? So let's look at what's going on within this Moiré structure. So you see we have these bright spots here alternating with darker spots. In the bright spots, we have every atom in the top layer has an atom in the bottom layer. So basically the bottom layer is completely eclipsed. In the darker regions, so you have two kinds of region. It's an AB region. There's roughly Bernal stacking in these regions. So in this region, you have an A atom in the top layer sits directly above a B atom in the bottom layer, and the B atom in the top layer has no partner. And when you do an STM topography, you only see the atoms that have no partners in the bottom layer. So instead of seeing a honeycomb structure, you're going to see a triangular structure like this. Now, if you go to the other side, we have BA, where the opposite happens, and it's the B atom, the A atom in the top layer that have no neighbor, so the triangle turns to the right. And here you see how this looks. You have the AA region surrounded by alternating AB and BA that are separated by a domain wall here. So it turns out that making an AA regime is very energetically costly. It costs about 20 millivolts per atom, whereas the AB regions and the domain walls are much cheaper. So immediately you notice that this will give you a periodic potential. When you look at the height profile, the AA region, because of this and costly energy costs, are a little bit higher than the other regions. So you can see this in STM, for example, and the density of state is higher again on the AA regions. So this is a recipe for creating a periodic potential. However, you will not get the simple band structure and the simple narrow bands that monotonically decrease in width with increasing period, because our band structure doesn't start out being parabolic, and it is Dirac instead. And you will see how very different this is from the standard expectation. So here is the red layer is on top of the green layer, reciprocal space. Here I plotted out all the 6 cones. So now here you have mini Brillouin zone. You have 2 mini Brillouin zones, one that comes from the K point and the other that comes from the K prime point. They have opposite chirality, these 2 mini Brillouin zones. And if you have perfect periodicity, or if the Moiré is a periodic structure, you can fold these mini Brillouins to the gamma point. The Hamiltonian now that describes this problem consists of 2 parts, the red layer, single layer Hamiltonian, the green single layer Hamiltonian. And if there is no hybridization between the 2 bands, if the interlayer hopping is 0, you simply get the band structure of 2 independent graphene layers. Now things become interesting when you can have tunneling between the 2 layers. In other words, where T perpendicular is finite. And in this case, this hybridization creates saddle points in the band structure, and now this gap becomes smaller by the tunneling energy here, by the interlayer tunneling energy. And this is very different from just imposing a plain periodic potential on this structure. And to see why is, first of all, these saddle points in the band structure translate into Van Hove singularities and the density of states. And this is where things can get interesting, because when you bring your Fermi energy into one of these, you're likely to create a correlated state. Now notice that when I decrease the twist angles, these Van Hove singularities or the saddle points are going to come closer and closer to each other. And there is finally a twist angle, which was dubbed magic angle, where this gap goes to 0. And it's roughly happens when the Moiré cell traversal time is equal to the interlayer tunneling time. And that's when you get a flat band. Now, this magic angle for standard parameters of interlayer hopping taking from bilayer graphene and standard Fermi velocity is about 1 degree. However, this number is not carved in stone because, for example, we can change the interlayer hopping by changing the distance between the layer. This was already demonstrated by the Columbia group, that when you apply pressure, you change this magic angle. And also you can change VF by, for example, screening. Now, this calculation was done by assuming that the hopping is uniform, and it's the same hopping whether you're an AA or AB. When you take the hopping on the AA lattice to 0, you get perfectly flat bands, as was recently shown. And here I have an animation that shows you what happens as you decrease the twist angle, and you're going to see, you see these Van Hoff singularities here, or the saddle points. We're approaching the magic angle, and boom, you have a flat band here. Now, of course, if you continue, the flat becomes broader. And that is because the flat band happens because of this very special hybridization condition, which was not taken into account in the simple model that I showed you at the beginning. Okay, so our experiment is STM. We all know how STM works. You bring a sharp tip to your sample, you measure the tunneling current, and you can change the bias voltage here. The tunneling current depends on 2 parameters, on the distance between the tip and your surface, and by rastering the sample, keeping the current and forcing the current to be constant and the bias constant, you can get a beautiful atomic resolution image of, in this case, graphene. The other quantity in this in the current is the density of states. And if you take the derivative of your current with respect to the bias voltage, you get out the density of states. And this is what it looks like. When you put graphene on graphite, it's a beautiful linear, vanishes at the Dirac point. In this case, we applied some gate voltage, so the Fermi energy is separate from the Dirac point, so one could study the physics of the Dirac point separately from the Fermi energy physics. Now, back in 2009, we were trying to look at something. At the time, it was called magnetic catalysis. Today, we call it Wally-Zeeman effect. And what we needed is to suspend the graphene, to do STM on a graphene layer that was not sitting on a substrate. And this was quite a tough call for exfoliated graphene because the samples were too small. So we decided, we asked our collaborator Jing Kong from MIT. She grew graphene on a nickel substrate, CVD graphene. Then we sent it to Kostya Novoselov at Manchester, who deposited on this nice TEM grid. And this is what it looks like. It's a 50 micron, a grid with 50 micron holes here. And when you look at it, you can see, you have a whole zoo of graphenes here. You have single layers and you have twisted bilayers. You even have tri-layers. So you can come with the STM and look at these samples. And we ended up not finding what we were looking for, but we found a very nice and interesting surprise. And that was these Moiré patterns. Here, for example, the period is 7.5 nanometers, which corresponds to an angle of about 1.79 degrees. This is the Fourier transform of your pattern. And then if you zoom into atomic resolution and compare the Fourier transform, you again can extract the exact same angle, 1.79 degrees. And then we did the IDV spectrum. So here is graphene and here is our twisted bilayer graphene. So we go from single layer, we have a kind of a V-shaped standard spectrum. We move onto this Moiré pattern and you see these beautiful peaks that appear, which we now know, which we later knew were the Van Hove singularities. So, and no matter where we went on this sample, these Van Hove singularities were right at the same spot. Then we could look at various angles. So this is again the same data for 1.79 degrees. Then you go to a larger angle, 3.5 degrees. The peaks are further away from each other. And at 20 degrees, they're outside of the field of view of our scan. So if you plot the separation of these Van Hove singularity peak as a function of twist angle, you get a monotonic dependence, which pretty much agrees with theory. But what's interesting here is you see that that there is a point before you reach 0 degrees, there is a point here where the separation goes to 0. And this is what later was called the magic angle. And this is the data at the magic angle. So this is 1.16 degrees. You see the Van Hove singularities have merged. Here at the Fermi energy, which is always the 0 in STM, you see a small gap, which we interpreted as a correlation effect at the time as a charge density wave. Of course, you can go beyond the magic angle, 1.1 degree, to a much smaller angle. This is 0.28 degrees. And you see how this pattern grows. The period now is 50 nanometers. And now the band becomes much broader. Notice that the AA region now has shrunk dramatically, and that's because of the high cost of energy to create them, and the cheap in the large Moiré system, it's much cheaper in terms of the strain produced to shrink these regions to basically almost a singularity.
Eva,
yes.
Sorry to interrupt. We have a question on the chat from GSGR, who is asking how to measure the twist angle with strain. So maybe you can quickly answer that.
So the strain is always there. What we do when we want to, I'm going to get to this, but you see what we do is we measure. If you have strain, of course, you don't have a constant twist angle. The twist, as you will see later, the twist angle changes, can change quite fast. But what we do is we take the average distances here and we extract an average twist angle if you have strain. And so yes, strain is a big problem in this system. However, it is not so serious in the CVD graphene system. CVD twisted bilayers are much more uniform than the ones that are generated by superposing graphene layers. So if you really want to get away from strain, maybe this is a way to go to control this. But CVD graphene has other problems.
Okay, and as we are stopped, I see that Evgeny, she also has a quick question maybe for you. Evgeny, can you ask your question? I think now okay, it seems like I cannot give you the speech. So the question, I'm gonna read it. It's why was this graphene grown on the nickel substrate, and does it make any difference?
Yes, because on copper substrate, it's very hard to get more than a monolayer. On nickel substrate, you can get bilayers and more depending on when you stop the growth. On copper, you can also get bilayer, but it's much more challenging. Now, why was it grown on nickel at the time? Is because, Jing Kong was an expert in nickel growth. at the time. We did not want to go for bilayers. We actually wanted to go for monolayers for what we were looking. So this was a little bit of a stroke of luck.
Okay, maybe we can then keep going. Thanks a lot for your answers.
Okay, so let's go to modern days, 2016, from the Emmanuel Tutuk's group. They invented this technique where you could actually control the twist angle, and it depends on the stickiness of the difference of the stickiness of graphene to boron nitride versus silicon dioxide. So you prepare a standard graphene on silicon dioxide, then you bring a boron nitride layer, you press a boron nitride layer on half of the sample, and you have to adjust the temperatures, so your graphene sticks, half of your graphene sticks to the boron nitride. You lift the boron nitride, it tears apart, and now you have two graphene layers that are part of the same crystal. You rotate the bottom crystal by an angle which you can control to a fraction of a degree, and then put your top layer on top of it, and then you remove the two, and voila, you have a twisted bilayer graphene. And of course, after that, you have to deposit electrodes and whatnot. And this is the work, this is a sample that came from Pablo Dario Herrera's group. So here they have twisted bilayer graphene on boron nitride. It's encapsulated in two boron nitride layers. Before I go on, let me just go to the nomenclature. What we are interested in is this flat band here, which is close to charge neutrality. It has an 8-fold degeneracy, 2 from spin, 2 from valley, and 2 from layer. So there are 8 subbands, degenerate subbands in this flat band. And the way we count the filling of this band, 1 carrier per moire cell correspond to filling one of these many bands, and it takes about 0.6 times 10 to the 12th electron per centimeter square, or in terms of gate voltage, 8.5 volts will fill one of these subbands. And so we can put 8 electrons in here, so we can count them, and there's various ways of counting them. So if you separate the conduction from the valence band, you count 1, 2, 3, 4 in the conduction, -1 to -4 in the valence band. You can also count them in terms of NS, which is what Pablo used. It's the number to fill the number of electrons to fill 1 of 4 of these bands, and in that case you can define a fractional filling. 1 electron per band in the conduction band is 1/4, 1/2, and so forth. In the valence band, it's 1/4 for 1 hole per band, and so on and so forth. So just to keep the nomenclature straight. And then in 2018, the MIT group announced this spectacular result that when you go around a filling of -2 holes per band, 2 holes per moire, you have an insulator, and we just go nearby, you see superconductivity kick in, and it forms a superconducting dome. Notice this temperature scale here is about 0.4 Kelvin, nothing to write home about. So why were people so excited about it? There were 3 reasons people were excited about it. First of all, we get an insulating phase flanked by superconducting domes, very similar to what we all know and love from high TC superconductors. Secondly, we have strong coupling. TC over the Fermi energy is very large, it's 10 to the -1, approaching the BEC boundary. And finally, and most importantly, is whereas in the high TC superconducting band structure, every point here requires a different sample because their doping is chemical, here you can go through the entire phase diagram by the turn of a knob. So even though TC was so small, like look, there are 2 orders of magnitude in TC, this looked like a very promising way to create superconductivity, possibly go to high temperature superconductivity, and most importantly, can it help us understand the mechanism of superconductivity in high TC superconductors? And of course, the obvious questions to ask, okay, we have in high TC superconductors, we have a pseudo gap phase where we have nematic order. Is this something that we can find in twisted bilayer graphene? Another question to ask is, okay, there's this strange metal phase where there's all these crazy things going on, linear and T-resistivity that persists down to the lowest temperatures, which people are struggling to understand. Do we have that in twisted bilayer graphene as well? So here is so using this technique of controlling the twist angle, we prepared a sample to look at with STM, and this is the same technique as I showed you before. The only difference being that we do not have a top boron nitride layer for the obvious reason that we need to the STM to reach the twisted bilayer graphene. So this is the topography here, and if you zoom in, you see beautifully in this AA region, you see the honeycomb structure, and you see the triangular structures on the AB and BA regions here. And of course, the next thing you want to do is to look at the density of state or to look at the spectra. And since we are able to gate this sample, which we are not able to do in the original experiment, we first take the Fermi energy way outside of the flat band. And you see that we have this beautiful flat band here. It's not that flat, it's about 40 to 50 millivolts in width. And then we take it to Fermi energy on the other side of the flat band, and again it looks the same. And then we bring the Fermi energy within the flat band. Here it's right at charge neutrality, and we see this beautiful pseudo gap opening, which tells us that we have a correlation gap here. Now, the pseudo gap physics was shown in 4 papers that appear pretty much simultaneously, and everybody saw this this opening of a pseudo gap when you bring the Fermi energy within this flat band. The other details are different in these experiments, but I'm not going to go into them here. Another thing that I wanted to point out, so when the Fermi energy is at charge neutrality, the spectral weight is pretty much the same on the full part of the band and the empty part of the band. This changes depending on how many electrons you throw into this flat band. And you can see this right away by when we do this, we called it a pseudo transport measurement. What we do, we park the energy of our tip at the Fermi energy, which means 0, and then we change the gate voltage or the carrier density. And you see immediately that you have these beautiful dips at every integer filling. This was also seen in the original paper by the MIT group, and it's seen by other transport measurement. Here is our own transport measurement, and you see that you get this nice dips in conductance every time you hit an integer filling of this band. The ones are not seen so very well here. We just have a paper on the archives that shows what happens here. Okay, so as I said, the spectral distribution between the full part and the empty part of the band changes with local doping. And here I have the topography, and this is mainly the AA region. This is sitting at charge neutrality. And then we take density of, we take spectra at every point in this AA region and calculate the spectral weight redistribution at every point, which allows us to calculate the charge at every point. I'm not going to go into the details of this technique. This is a charge spectroscopy technique. If you're interested, I'm going to go through it in the question part, because it's going to take about 2 slides to do this. But the bottom line, the bottom result is that we are able to resolve the local charge within here. So this is a charge spectroscopy. And what we see here that is the charge, there is a spontaneous reorganization of the charge. Red here is negative, so it corresponds to 1 electron per moire. Blue is positive charge, 1 hole per moire, and you see that you have a quadruple spontaneous redistribution of the charge when we sit within the flat band. Now, if we do the same thing over a larger scale, so here you see the C6 symmetry of the sample, and if we look at the charge spectroscopy, these quadruples of charge rearrange themselves, so we have stripe with 1 electron per moire in red here and 1 hole per moire in blue here. So clearly this looks like we have nematic charge order. Now just to make sure that this is not a simple strain effect, for example, if we do the same experiment in the full or empty band, we see none of this charge redistribution. If we do the same thing at an angle that's not a magic angle, for example, 1.5 degrees, where we no longer have a flat band separated by gaps from dispersive bands, this whole physics goes away. Importantly, in the same sample, the charge nematic order disappears above 35 Kelvin or above 8 Tesla. So clearly this is a property of the state, the correlated state that is created by bringing the Fermi energy into the flat band. So going back to our comparison with high TC superconductors, where are we standing here? So we have a pseudo gap phase, yes. We have nematic order, yes. And so this is similar to what we have here in the high TC superconductor. And as in the high TC, maybe what we are seeing here is a precursor of low T superconducting state. I should mention that all our experiments were done above the superconducting temperature. They were done at about 4.5 Kelvin. Now, there are many people, including our group, are working on this question, and there's some evidence that there is also linear in T conductivity that goes down to low temperature. So possibly the strange metal behavior is here as well. Okay, so this is very wonderful, but now it's not as ideal as one might think. And as you've already seen in previous talks in this conference, the fly in the ointment is the twist angle disorder, which is mainly due to strain. And you can see that in Raman, AFM, and nanosquid, as well in STM, very clearly here. There is the period changes as a function of position, and in this case, quite rapidly. With STM, fortunately, we can go and look for a place where the twist angle is most uniform. So, for example, a twist angle change of about 0.05 degrees at a filling of 3 changes the local filling by 0.3, which means that twist angle disorder is really a big problem, especially if you want superconductivity, unless you have a percolating path across the sample, which is exactly at the magic angle, you're not going to see superconductivity. How am I doing time-wise? You're muted. I can't hear you, you're muted.
You're doing well. We have half an hour more. That includes some questions, but there are some that you can take now.
Oh, okay, great.
If you want, I see a question from Hélène Bouchia. I will try, Hélène, to give you the mic, but for some reason I can't. I think I don't have the rights. So I will just read her question. So Hélène is asking did one measure the low temperature magnetotransport on these very low angle twisted bilayer graphene samples?
You mean the point? I don't know what you mean by low angle.
Yes, it's the one you were
the answer is yes. There are quite a few experiments. There's certainly at the magic angle, are you talking about the magic angle or below the magic angle? At the very low, there are a few experiments from the ETH group, from Klaus Ensling's group. There is a measurement, TM measurement from Philip Kim's group, and there are STM measurements, but there are not very many. This is a fantastic way to go forward. Helene, I'm not sure that this is what you meant, but yeah.
So,
okay.
Okay, I'm sorry, I'm the intermediate there because I still don't have it would be great, Merce, if I can have the rights to invite people to speak, because there is a problem here. So she's precising her question. She's asking if there is something like AB oscillation, for instance. Okay, now I can make her speak. Okay, wait.
Okay, thank you.
Yeah. Okay, Hélène, now I think you can unmute and speak, if it works. Okay, I see you're muted. Okay, well, maybe we can skip that for the moment and come back on it a bit later. Meanwhile, and I just see there is another question from Ilya Goikman. Ilya, do you want to ask your question? Okay.
I'm sorry, it probably was a mistake.
Okay. I saw you raise your hands.
Yeah.
Okay.
Sorry.
And last one from Teldo Pereira. It disappeared as well. Okay, so who's our Teldo? Do you have a question? I see you raise your hand. Okay, so it was maybe another mistake. Okay, well, let's keep going then.
Okay, so let's we've seen that twisted bilayer graphene is not the last word in this field. Maybe we can create flat bands in other ways. As I hinted at the beginning, strain would be a good strategy. So here is undistorted graphene. All the three hoppings are the same when you and the interatomic distance, the three interatomic distance, nearest neighbor distance are all the same. Now, if you introduce strain, then and if the strain is not too large, you can express the nearest neighbor hopping in terms of the ratio between the stretched bond to the original bond, and this is this exponential expression here. Beta here is the Gruneisen parameter, and then you get a Hamiltonian where VF actually depends on position, and we all know that when that happens, you can apply first order perturbation theory, and what you get is an emergent gauge field here, which I called A here, which is like a vector potential. Notice the psi here has opposite signs in the two valleys, and this is very important. So A is basically a vector potential, which gives you a pseudo-magnetic field. When you take, if we have a finite curl, you get a local pseudo-magnetic field that has opposite signs in the two valleys, and this is very important. So you get a pseudo-magnetic field, but the signs are opposite. Now, what are the experimental implications of that? So let's look at the density of state. The band structure in the presence of a regular magnetic field is the same as in the presence of the pseudomagnetic field. You have these Landau levels with the Landau level at 0 energy here. However, the only difference is that whereas in a real magnetic field that breaks time reversal symmetry, the sign of B is the same in both valleys. Here it has opposite signs. However, the density of states really doesn't care about the sign of your field, so it's going to be exactly the same as if you had a regular magnetic field, and you're going to have the regular sequence of Landau levels, which goes like the square root of the pseudomagnetic field this time and the Landau level index. Now, what's important to realize when you have whether you have a real or a pseudomagnetic field, the wave function in the zeroth Landau level, the wave function is valley polarized. So if the wave function in the K valley is all sitting on the A sublattice, and the wave function in the K prime valley all sits in the B sublattice. So it is valley polarized. Now, when you have an external magnetic field, this is totally irrelevant because we can't tell the difference. However, with a pseudomagnetic field, if you're able to separate the field up and field down, as I showed that you can do, you can actually see the pseudomagnetic, this valley polarization. So this is just graphene is a membrane. It's a thin membrane. It is stiff. It has very high stiffness in plane, but it's very soft out of plane. And it is well known from membrane theory that if you have such a membrane and you apply compressive strain, you can create all these different buckling patterns, out of plane buckling patterns. And depending on the substrate that you use and the Young's modulus versus the bending modulus, you can create different patterns. And that means that you can do this with graphene as well. And we were actually able to do this. We have a graphene layer that's deposited on a niobium diselenide sample, and after heat treatment, there were two ripples that were pinned, which were able to apply compressive strain. And the bottom line is at the end of the day, these are the two ripples, and this is zooming in to this buckling structure. We obtain a beautiful periodic strain-induced hexagonal buckling mode. And it's beautifully periodic. Here is what it looks, the out-of-plane profile, it's about 1.5 angstrom. The period in this case is 14 nanometers. We have periods running from 9 nanometers to 25 nanometers. And this gives us a pseudomagnetic field, a periodic pseudomagnetic field, which actually oscillates up and down. And in the topography, here is what it looks like. These are the peaks, and here are the troughs. So if we look at the DIDV spectrum, if we take the DIDV spectrum on one of these peaks, we get this beautiful pseudo-Landau level structure. Now we can fit it if we fit the energy sequence as a function of square root of the Landau level index, we can extract the pseudomagnetic field, which is about 108 Tesla. It's a huge pseudomagnetic field that comes from this compressive strain. Now, this is a band structure that we get. Of course, something like this will give you a flat band. This is a simulation of the band structure for this pseudomagnetic field, and you get a sequence of flat bands. if in principle, if you can bring the Fermi energy in these flat bands, you should be able to open a pseudo gap here. In this particular sample, we were not able to do it because the substrate was niobium diselenide. It was a conductor, and you can imagine that we were not. The reason for doing this experiment was not to look at the buckling transition. However, we got a lucky break here with this. Now we have a new experiment where we put the graphene on boron nitride, and we saw indeed the pseudo-magnetic fields. We were able to bring the Fermi energy within the peak here and see a pseudo gap open. Now, in terms of the sublattice polarization, this is an atomic. We're going to go to atomic resolution map in the n equals 0 level. And if you remember, the K, the wave function, the K point lies on the A sublattice and the K prime point lies in the B sublattice. Here we have the pseudomagnetic field is 108 Tesla here, and around here it is much smaller. It's around something like 50 Tesla. Because the area is much larger. Remember, we're not breaking time reversal symmetry, so the net pseudomagnetic flux has to be 0. So we have an oscillating field that goes from positive to negative. And so, so here you'd expect the wave function to sit on one sublattice where the field is positive. Here you'd expect it to sit on the other sublattice. So let's see what's going on. Here we're sitting on the apex here, on the crest, and we see indeed, we no longer see the hexagonal structure, we see a triangular structure that is a triangle that's pointing down here, that's telling us that the wave function is sitting on one of the sublattices. And now we're going to the trough region, and now the triangles point the other way. If we go to the transition region in between the two, we recover the honeycomb structure here. So, so this tells us that we have the direction of the pseudomagnetic field is opposite in the two sublattices. Okay, so what next? Okay, so I've shown you two systems in which we can create flat bands. One is a magic angle twisted bilayer graphene, but that has a problem that it requires very delicate tuning over large areas of the sample. At the moment, this is very difficult to control. So we have to find ways of improving that. In the second part, I showed you another way of creating flat band is by periodic buckling superstructure or periodic supermagnetic field. However, it's very difficult to control the geometry here. So what's next? The next thing to try is to have an artificial strain superstructure. For example, have an array of pillars. In this case, we have gold on boron nitride, and the distances here are quite large, 2 micron between the posts, and their height is about 17 nanometers. We're able to induce about 10% of strain. And the reason this is interesting is that we have more control. The geometry is controlled, whereas in twisted bilayer graphene, you can only get a triangular geometry. When you do this, you can get whatever geometry you want. And of course, the strain is controllable because it will be controlled by the ratio of the height of these pillars to their separation. So we have done this with this structure here, and we found a very nice pseudomagnetic field. Here we have 8 Tesla. You see the pseudo-Landau level give you pseudomagnetic field of 8 Tesla. When you go on top of these pillars, the fields become huge and the strain becomes huge. It gets close to the breaking point of graphene, close to 20 20%, and very interesting things happen on top of these pillars. But the bottom line is perhaps this is the way to go next, to take this direction forward. And of course, the big questions that still remain is what is the mechanism of superconducting in twisted bilayer graphene? Many people are working on this, and there are many theoretical papers on this, and we hope to get an answer soon. And the question is if we understand the mechanism of superconductivity in twisted bilayer graphene, is it going to help us understand superconductivity in high temperature superconductors? And also, can we create high temperature flat band superconductivity? And that brings me to the end of my talk. This is my summary. These are the two topics that I talked about. Moiré patterns give rise in twisted bilayer graphene, give rise to Van Hove singularity. Magic angle, you get a flat band. And if you bring the Fermi energy within it, you get a nematic order and you get a pseudo-gap state. A flat band with a buckle here. You get a periodic pseudo-magnetic field of amplitude of about 108 Tesla. You see sublattice polarization corresponding to a pseudo-magnetic field up or down. And so this is the mechanism of making flat bands without breaking time reversal symmetry and without fine tuning. And finally, and most importantly, here are the people who did the experimental work. On the right here, Christian Haule and the group of Francois Peters helped with the theory. And boron nitride was obtained from our Japanese collaborators, and the graphene on iron diselenite was sent to us by Andrei Geim's group. Thank you for your attention.
Thanks a lot, Eva, for this beautiful talk. I see that we have a couple of questions, so maybe we could start right away with Shenli Wang. I will normally now give you the speech. Shenli, I don't know if you can speak.
Can you hear me?
Yep.
Professor Andrei, thank you for your talk. So you show a pseudo-magnetic field of 100 Tesla. Shouldn't that correspond to a magnetic length of about 2 nanometers? Why is it on the last few slides I saw like 8 to 10 nanometer spacings?
Yes, the pseudomagnetic field does correspond to 2 nanometers. Now, what last slides are you? Oh, no, okay. Yeah, okay. So this is the buckling period. That is determined by the buckling period. The pseudomagnetic field. Now, if the magnetic length, in order for you to have a reasonably well-defined pseudomagnetic field, the magnetic length has to be smaller than the scale over which the pseudomagnetic field changes. Otherwise, it's not well-defined. So that's why. So this changes on the order of maybe 10 nanometers here. So 2 nanometers is enough. You have to be able to fit a Landau orbit within a region of almost uniform pseudomagnetic field. Right. Good question. And we address this in great detail in this paper.
Okay, so thanks a lot. Let's move on. I try to go through the question in a chronological order. So now it's Maximilian Kogel. Maximilian, can you?
Yeah.
Yep.
So thank you for the talk. I have a question regarding the buckling. How was that achieved in that periodic manner? It looks like it's a profile. It looks like a Moiré pattern, and I think you put the graphene on top of diselenite. Was that the basic thing that make it buckle, or what's the magic behind it?
Okay, no, it is not. It works on everything. So you start out. Okay, when you put the graphene a membrane on top of a substrate, there is almost no getting away from wrinkles. Now, normally you'd want to get away from the wrinkles to have a uniform, for example, twist angle. But in this case, we made lemonade out of lemon. We had these two wrinkles. Okay, I mean, we didn't do it. This happened spontaneously. Now, these wrinkles were presumably filled with gas. Now, when we did thermal cycling, they blew up, and then when we cooled it down, they collapsed. And I don't have the figure here, but it's in the paper. And we can see by how much they collapsed. And because they couldn't move outwards, they pushed the layer inwards. You need a compressive strain, not tensile strain, to create these structures. So we need compressive strain. So see that it's pushing in, and we could calculate exactly by how much it pushed in that it was kind of the right thing. Now, very good question. Why am I calling this a buckling structure rather than a moiré? That is because the moiré period, when you have two different substrates, for example, niobium diselenide and graphene, the lattice constant are very different. They're different by almost a factor of 2, which means that the moiré pattern is going to be extremely small. It's going to be a nanometer or so, whereas these periods are much larger. Also, the period changes monotonically with distance from the apex here, from the point where the two ridges meet. So this was about 14 nanometers. When you go far away, it goes up to 28. Here it's about 9 nanometers, and that clearly tells us that it has to do with the strain, with the compressive strain that comes from these ridges, just by geometry.
Okay, so I see there are a lot more questions. Let's try to go through some of them. Teldo Pereira, I see you raise your hand, and I think you can talk now. Teldo, are you here?
Podemos?
Ah, yeah. Ah, okay. I don't know if Teldo can hear us. Maybe I will go to the next one. Antonio Manesco, I give you the mic now.
Yeah. Hi, thanks. First, thanks for the talk. And I'm wondering if for these nanopillars structures, you also have any indications of correlation effects?
Oh, you mean the nanopillar data here?
Yeah.
No, we do not. And the reason is we were not able, here these pillars were gold pillars, so we were not able to very easily dope the sample. Now, we also did a transport measurement where we saw some very interesting effects that may have to do with it, but we still need to figure out what's going on. So the simple answer is no, we don't have data, but that doesn't mean that it cannot be done. It should be possible to do.
Okay, thank you.
Next question from Ligo Ma.
Hello, so I have 2 quick questions on the charge order phase and twisted bilayer graphene. So first thing is, did you see any strain and topography image? And another question is that at high field, where pneumatic order disappear, is pseudo gap still present?
Okay, so first of all, strain. I'm showing you, this is the data. So we can find places where the strain is huge, but we can also find places where the strain is small. So, you know, because STM is a local measurement, if you move away from this region of the strong strain, you can pretty much see what's going on in the absence of strain. So some samples are more strained than other, but yes, we can see the strain pretty obviously. And the pseudo gap does disappear, yes, at above 8 Tesla. It depends on the sample. In one case it was 8 Tesla, in the other case it was 10 Tesla, yes.
Yeah, excellent, thank you.
Okay, next question from Gang Lee.
Hi, my question is about the STM measurement on the twisted bilayer graphene. There are several models to calculate the band structure, and they predict different Van Hole singularity separations at charge neutral point. So how do you match your experimental and theory?
Okay, so let me go back. Oops, I'm going the wrong way. So the theory was done by Antonio Castroneto and collaborators, and it's very simple, and it works beautifully. I mean, it's just doing it's just from tight binding. What I showed you in the theory here. Here, right? This is what you mean. It's simple tight binding. And that's all that went into it. And intuitively, I showed how this happens. Look here. It's simply the crossing, and okay, here it is. So you see, it's the Van Hove singularities are the energy separation between the Van Hove singularity is simply the distance between these saddle points, and it's given by the point where the two cones intersect minus 2 times the hopping, the interlayer hopping. So it's a pretty straightforward way to do it, because k theta goes like sine theta over 2, 1 over sine theta over 2. So even just from this simple thing, you can get the relationship. It doesn't matter. It's not more complicated than that.
Okay, I think we have time for one last question from Xing Chen about another intrinsic superconductor.
Yes, I'm interested in the niobium diselenide. I'm wondering, with this pseudo-magnetic field, would you affect the superconductivity of niobium diselenide underneath?
Okay, so the reason we had this sample is that we did want to look at the interaction of the superconductivity with graphene. And unfortunately, this sample was not superconducting. So, so all it did for us is give us the possibility to create a buckling structure, but it was not superconducting. So of course, we would have loved to have a sample that was superconducting.
Oh, so you expect an effect with this added on top layer of graphene?
If the substrate is superconducting, yeah, for sure. I think it's going to be very interesting. I mean, you know, you want to look at vortices and things like that. Yeah, you want to look in the core of a vortex.
Ah, great, thank you.
Okay, sure.
Okay, well, I think it's time to go on. So thanks, Eva, again for this very nice talk. And thanks to all of you for coming and having all these questions. We will zoom out now, and the next seminar will start actually in 15 minutes. And it will be given by Lenny Bascones from Madrid about interaction in twisted bilayer graphene. So yeah, stay tuned. Thanks again.
Okay, thank you.
Thank you very much, Eva. Thank you, Anton. I'm gonna end this meeting now and I will see you all in 15 minutes. Bye-bye.